Hello and welcome. In this lecture, we will learn about sequence in Rn. So outline of our lecture is, first we see sequence in R, then we see about sequence in Rn, then we see about examples on sequence in Rn. After that, we see convergence of sequence in Rn, and then finally we see problems on sequence in Rn. So first of all, we define sequence in R. So let us write the definition. A sequence in R is a function from set of natural numbers n to the set of real numbers R. Let x be a sequence of real numbers, then x is a function from set of natural number to the set of real numbers. Let x of n equal to xn for all n equal to 1 2 3. So this is the sequence function, and x of n is equal to, this is the value of xn, and this term we called as the nth term of that sequence. Okay, this sequence we can denote by another notation. We can use this notation to denote sequence, or we use this notation. Into the curly bracket we write xn, and n runs from 1 to infinity. N is a natural number, small n is a natural number, it runs from 1 to infinity. Okay, so sequence xn is nothing but infinite tuple, uh, ordered infinite tuple, whose first term is x1, second term is x2, third term is x3. In this way we can write infinitely many terms of this sequence, where xi for I equal to 1 2 3 comma dot 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 are called as terms of a sequence xn, and xn is called as nth term of sequence xn. If we know the nth term of sequence, then that sequence will be completely known to us. If the number of terms in sequence xn are infinite, then the sequence is called as infinite sequence. There are different types of sequences, and these types of sequences, due to the different behavior of nth term xn of that sequence. So let us define convergence of a sequence in R. Definition: a sequence xn is said to be convergent at a real number a if, for any given epsilon greater than 0, there exists a big natural number n naught belongs to n such that such that such that mod of xn minus a is less than epsilon for all n greater or equal n naught. The meaning of this is sequence xn is said to be converges to a if the distance between the terms of sequence and the point and the real number a becomes smaller and smaller when n becomes larger and larger. Okay, so here a is called as the limit of a sequence xn, and it is denoted by limit of xn is a as n tends to infinity. So here we also we can say that the terms of sequence xn approaches to a when n becomes larger and larger. Okay, so sequence xn converges to a if and only if the distance between terms of sequence and real number a becomes smaller and smaller. Tends to a means distance, so mod of xn minus a, geometrically it represents, we know that geometrically it represents a distance between xn and a. So when this distance become approaches to 0, when this distance becomes smaller and smaller in R, then we say that the sequence xn converges to a. The geometrical meaning is uh, geometrically a real number a is said to be limit of a sequence xn if whenever values of natural number n becomes larger and larger, then the distance between terms of sequence xn and real number a becomes smaller and smaller. So this is the geometrical meaning of a convergent sequence. Okay, so we represent a one convergent sequence of a real number geometrically. So let us take one sequence xn n equal to 1 to infinity, where xn is equal to 1 upon n. Okay, so here we write some terms of that sequence and we plot all these terms on the real line, and we observe the behavior of that sequence. Okay, so here are some terms I have written for n equal to 1 2 3 dot dot dot. The terms of sequence are x1 x2 xn, and the values of these terms of sequence are 1 1 half 1 by 3 dot dot dot. So like this. So I have written I have written 23 terms of that sequence. We can the sequence has infinitely many terms. The sequence has infinitely many terms, but I have written here only 23 terms, and I have plotted all these terms on the real line. So see here, so this is our real line in plus infinity. Here it is minus infinity. Okay, so 0, suppose 0 is here, and here is a number 1. So this is unit distance. Okay, and so where is the first term of that sequence? The first term of that sequence is 1. We plot here 1. Second term is 1 half. 1 half is here. Third term is 1 by 3 is here. Fourth term is 1 by 4 is here. So you observe that the terms, so green dots, they are terms of sequences, and these terms of sequences, they are the terms of sequence, they are approaching towards one number, that is the zero number. So see here, we observe that the terms of sequence, they are approaching towards 0. See here. Okay, so we can say that the terms of sequence xn equal to 1 upon n approaches towards 0. Therefore 0 is the limit of that sequence 1 upon n. So see, okay, so approaching towards 0. So here terms of sequence 1 upon n approaches to 0 as values of n becomes larger and larger. Therefore we can say that the limit of sequence 1 upon n is 0 as n tends to infinity. Therefore we can write limit of 1 upon n as n tends to infinity is 0. The meaning is the terms of sequence 1 upon n approaches to 0 when n becomes larger and larger. N means the suffix of term xn. Okay, it becomes larger and larger, means then terms approaches to the 0. So see the examples on sequence in R. So let us see one example on sequence in R. So let xn be a sequence of real numbers where xn equal to 1 upon n for all n belongs to n. The terms of sequence xn are, first term is 1. So if I put n equal to 1 2 3 4 dot 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 in this equation, so then you can find, then you will get the terms of that sequence. So first term is 1, second term is 1 upon root 2, third term is 1 upon root 3, fourth term is 1 upon root 5, fifth term is 1 upon root fourth term is 1 upon root 4, fifth term is 1 upon root 5, comma dot dot dot. We can write infinitely many terms of that sequence. Okay, so we show that this sequence converges to a real number 0. That is, we show that limit of sequence xn as n tends to infinity is 0. By definition, we show that for any given epsilon greater than 0, there exists a big natural number n not belongs to n, such that such that such that the distance between the terms of sequence and the real number 0 becomes smaller and smaller when n becomes larger and larger. Okay, that we will show. So consider the inequality mod of xn minus 0 less than epsilon. But we observe that so minus 0 is meaningless. Therefore, this is implied and implied by mod of xn is less than epsilon. But what is xn? Xn is 1 upon root n. Therefore, it is mod of 1 upon root n is less than epsilon. But this is implied and implied by, so as see here, 1 upon root n is always a positive number. Therefore, mod of positive number is that number itself. Therefore, it is implied and implied by 1 upon root n is less than epsilon. So, if we square this implies and implied by 1 upon n is less than epsilon square. Take a square on both sides. Okay, and if we take the reciprocal, it will imply and implied by n greater than 1 upon epsilon square. So now from this inequality we can choose our n naught to be greater than 1 upon epsilon square. So if I choose our n naught like this, then this inequality will give our result mod of xn minus 0 is less than epsilon. The meaning is that the terms of sequence xn and number 0, the distance between terms of sequence xn and 0 becomes smaller and smaller, and it is true for all those n which are greater than n naught. So in this way, the sequence 1 upon n is converges to a real number 0. Okay, so now we see the sequence in Rn. So let us write the definition of sequence in Rn. So sequence in Rn is a function from set of natural numbers n to the Euclidean space Rn. So it is also a function. Sequence in Rn, it is also a function. Suppose, so let x be a sequence in Rn. Therefore, x is a function from set of natural number to the set of Rn. Set Rn. So define this function like this: x of m is equal to xm for all m belongs to n. Here xm belongs to Rn. Therefore, xm has n components, and important is, and each component is again a sequence of real numbers. So here xm is so xm is the general term of that sequence. Okay, general term of that sequence, and this general term has n components, and each component, so here first component is xm1, second component is xm2, third component is xm3 comma dot dot dot, and nth component is xmn. So all these components are again a sequences in set of real numbers. Okay, so this is one sequence, this is our second sequence, this is our third sequence. So in this way, so this is our mth term of sequence xn in Rn. Okay, so here xmi is a sequence of real numbers, so means components are sequence in real numbers. So this sequence we denote by notation. This is the first notation, and this is our second notation to denote the sequence xm in Rn. So into two curly brackets xm, we write xm, and m runs from 1 to infinity. Okay, where xm for m equal to 1, 2, 3, dot 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 are called as terms of sequence xm, and xm is called as mth term of sequence xm. Each term of sequence xm is an ordered n tuple in Rn. Each term of sequence xm is an ordered n tuple in Rn. That is important. Now we define the convergent sequence in Rn. So write the definition. A sequence xm in Rn is said to be convergent to the point A belongs to Rn if for any given small number epsilon greater than 0 there exists a big natural number m naught belongs to n such that norm of xm minus a is less than epsilon for all m greater equal m naught. The meaning is that the sequence xm in Rn is said to be converges to the point A in Rn if and only if if and only if the distance between terms of sequence xm and point A becomes smaller and smaller when the values of m becomes larger and larger. That is the simple meaning. Okay, or we can say that uh, sequence xm in Rn is said to be converges to the point A in Rn if and only if for any given epsilon greater than 0 there exists a big natural number m naught belongs to n such that all terms beyond the terms x m naught are within the distance epsilon from the point A. That is also very important. Okay, so here A is called the limit of a sequence xm and it is denoted by limit of xm as m tends to infinity is equal to A. So here also we can say that limit of that sequence xm is A, means terms of sequence xm approaches to A when m becomes larger and larger. Okay, so sequence xm, so see here sequence converges to A if and only if the distance between terms of sequence and point A becomes smaller and smaller. So norm means distance. Norm of xm minus a means distance between xm and A becomes smaller and smaller. Okay. So geometrically, point A in Rn is said to be the limit of sequence xm in Rn if whenever values of natural number m becomes larger and larger, then the distance between terms of sequence xm and point A becomes smaller and smaller. So this is the geometrical meaning of convergence of a sequence. Okay, so let us we represent geometrically convergence sequence in R2. So let us take one sequence xm be a sequence in R2 defined as xm equal to 3m minus 1 upon m, comma 4m square minus 1 upon m square. So as xm is a sequence in R2, therefore its mth term has two components. So first component is a sequence in R, second component is also a sequence in R. Okay, so let us find the terms of sequence xm. So first term, how to find first term? If I put m equal to 1, you will get a first term of sequence xm. Okay, so and if I put m equal to 2, then you will get the second term of that sequence. So each term of sequence xm is an ordered pair in R2. Is an ordered pair in R2. So in this fashion, we found here 15 terms of that sequence. Okay, so first term of that sequence is 2 comma 3. Second term of that sequence is 5 by 2 comma 15 by 4. So see here, all these points I have plotted on the R2 plane and we observe that the behavior of that sequence. Okay, so see here, so this is our x-axis, y-axis, R2 plane, and we plot all these points, means all the terms we plot the 15 points, first 15 points of that sequence. Okay, sequence xm here. So first point is here 2 comma 3, second point is here, second point means second term, third term is third term, fourth term, fifth term, fifth, seventh, sixth, seventh, eighth. So we observe that the terms of sequence, they are approaching towards one point. And what is that point? So see here, they are approaching towards one point, and that point is 3 comma 4. Okay, so the terms of sequence, they are approaching towards the point 3 comma 4. Therefore we can say that this sequence converges to the point 3 comma 4. Okay, so thus the sequence xm in R2 where xm is equal to 3m minus 1 upon m comma 4m square minus 1 upon m square converges to the point 3 comma 4 in R2. Okay, thus limit of sequence xm is 0.3 comma 4 in R2. Okay, so now let us see the theorem on sequence in R2. That is important theorem. This theorem, we state this theorem first. Let xm be a sequence in Rn given by xm equal to xm with n components. First component is xm1, second component is xm2, third component is xm3, comma dot dot dot, and nth component is xmn. So all these components are nothing but the sequences in R, and this ordered n tuple is an ordered n tuple. Okay, so what we have stated here, let xm be a sequence in Rn given by xm equal to ordered n tuple, where xm is then xm is convergent in Rn if and only if each of the component sequence xm each of the component sequence xm1, xm2, xm3, dot 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 xmn is convergent in R. So see here, while proving this theorem, we have to prove this theorem in two parts. Okay, so as here this theorem is if and only if type, therefore we have to prove this theorem in two parts. So in first part, we assume that the sequence xm in Rn converges to a point A. Okay, we assume that sequence xm is convergent sequence, and then we show that, and here we show that the each component sequence of that sequence xm is convergent. Okay, so assume that the sequence xm in Rn converges to a point A equal to a1 comma a2 comma dot 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 comma an in Rn. Okay, by definition of convergence of sequence in Rn, we have for a given epsilon greater than 0, there exists a natural number m0 such that the distance between terms of sequence xm and point A becomes smaller and smaller when for all or we can say that when m becomes larger and larger. Okay, so consider the uh, consider okay, so consider this thing. So see here, norm of, so this is we have, what we have is this thing. So norm of xm minus a is less than epsilon. So norm of xm, so xm is here, okay, a is here, and their subtraction and their norm. So this thing is known to us. What will be this thing? So this thing will be this thing, square root of xm1 minus a1 square plus xm2 minus a2 square plus dot 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 plus xmn minus an square and less than epsilon. Okay, so this is nothing but, so what does it represent geometrically? It represents geometrically distance between a vector xm and vector a. And how to write distance between vector xm and a? The we write that distance like this, so by distance formula. Okay, and the distance is less than epsilon, and it is true for all m greater equal m naught. But we know that the mod of xmi minus ai is equal to square root of, it is nothing, it is same as square root of xmi minus ai square. This is only square root of only one term. If we add n terms in the square root, then this term becomes less than this term. Okay, so and but from this step, this square root is less than epsilon, therefore finally we can say that this modulus is less than epsilon. Okay, so thus mod of xmi minus ai is less than epsilon for all I equal to 1 to up to n for all m greater equal m naught. So see here we observe that the terms of sequence xmi and the point ai is larger and larger when m becomes here the terms of sequence the distance between the terms of sequence xmi and the point number ai, the distance between terms of sequence xmi and number ai becomes smaller and smaller when m becomes larger and larger. So this is nothing but the convergence sequence. So in other words, we can say that the sequence xmi is converges to ai for all I equal to 1 to n. This means, so see here sequence x, so limit of sequence xmi is ai. So limit exists here as m tends to infinity. So each of the component sequence xm1, xm2, xm3, xmn is convergent in R. Thus we have proved our first part. Whenever sequence xm convergent, then its component sequences are also convergent in R. Okay. Now we see the second part of this theorem. In second part, we assume that all component sequences are convergent, and then we show that the sequence xm is convergent. Okay, so assuming that each of the component sequence of sequence xm is convergent, where xm is mth term of sequence xm, and his mth term has n components. First component is xm1, second component is xm2, third component is xm3, and nth component is xmn. Okay, so and each component is a sequence in R, and we assume that each of these sequences is convergent. Okay, so that is limit of xmi as m tends to infinity is equal to ai, and this ai exists for all I equal to 1 to n. That is, all sequences are convergent. Okay, for any given, therefore for any given epsilon greater than 0, there exists a big natural number mi belongs to n, such that whenever distance between terms of sequence xmi and ai becomes smaller and smaller when m becomes larger and larger. Okay, so let us take m naught to be a number which is maximum of all these mi's. So if I take m naught like this, then what happens? So xmi minus ai is less than epsilon upon n, and this will be true for all m which are greater equal m naught. Okay, so this inequality is true for all m which are greater equal m naught. Sorry, all m which are greater equal mi. Therefore, this will be true, and if I choose, and we are taking m naught to be maximum of all these mi, therefore this inequality will be true for all m which are greater equal m naught. Okay, and this is true for all I equal to 1 to n. Okay, so if I take a square on both sides in this inequality, then we have into bracket xmi minus ei square is less than epsilon square upon n for all m greater equal m naught, and for all I equal to 1 to n. So now consider this norm of xm minus a, but norm of xm minus a is nothing but this square root of xm1 minus a1 square plus xm2 minus a2 square plus dot 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 plus xmn minus an square. And we know that each of these terms in the square root is less than epsilon square upon n. Therefore, instead of this term we put in epsilon square upon n, and we put here greater than sign. Okay, so this term is greater this. Okay, so epsilon square upon n is greater than first term, epsilon square upon n is greater than the second term, dot dot dot, epsilon square upon n is greater than this last nth term. Okay, so this is the addition of epsilon square upon n, and it is how many times? It is n times. So we write here n into epsilon square upon n into the square root. So n will get cancelled, and into the square root, it is left only epsilon square, and square root of epsilon square is epsilon. So finally we can say that this norm is less than epsilon. So see here, norm of xm minus a is less than epsilon, and this is true for all m greater or equal m naught. So this is nothing but in other words, we can say that the terms of sequence xm uh, and the point a, the distance between terms of sequence xm and the point a becomes smaller and smaller when m becomes larger and larger. Thus, this shows that the sequence xm is convergent sequence. Okay, so that is very important theorem, and we have proved that theorem. Okay, now let us take some examples on sequence in Rn. Example number 1. Let xm be a sequence in R2 defined as xm equal to 1 upon m, comma m minus 1 upon m. Here component sequence 1 upon m equal to 1 to infinity is a sequence of real numbers, and it is convergent sequence and converges to real number 0. Also the component sequence, second component sequence is m minus 1 upon m, is a sequence of real numbers, and it is convergent sequence and converges to a real number 1. Thus all component sequences of sequence xm are convergent. Therefore the sequence xm itself is also convergent and converges to the point 0, 1 in R2. Okay, so examples on sequencing R2. So see here, so let us take one example. Next example, question number 1. Check the convergence of sequence xm in R3, where xm is the general term of sequence xm, and this general term has 3 components. Okay, so each of these 3 components, they are sequences in R. Okay, and we have to check the convergence of this sequence with this general term. So here we check the convergence of each of the component sequence xm. Just we check the convergence of these component sequences. If all the component sequences are convergent, then sequence xm is convergent, and if any one of the component sequence is not convergent, then the sequence xm will not be convergent. Okay, so see here, first component sequence is xm1, and it is 4m minus 3 upon 8m minus 9, and if we take the limit of that term as m tends to infinity, then you will find that limit is 1/2, means that limit exists. Therefore this sequence is convergent and converges to the point 1/2. Okay, so first component sequence is convergent. Now consider the 1 minute. Now consider the second component sequence. Second component sequence xm2, 3m square upon 4m square plus 3m plus 1. Okay, and here also we have to find the limit of that sequence, and find the limit of that sequence as m tends to infinity, and we observe that that limit will be 3/4. Okay, so limit exists, therefore this sequence is convergent and converges to the point 3/4. Third component sequence is xm3 equal to 7 upon 6m square plus 5, and here also we find the limit of that component sequence as m tends to infinity, and observe that that limit is 0. Therefore, this third component sequence is also convergent and converges to the point 0. Thus, all component sequences are convergent. Therefore, sequence xm in R3 is also convergent and converges to the point 1 half, 3 by 4, 0. Okay, so limit of sequence xm as m tends to infinity is 1 half ordered triple point in R3 whose components are 1 half, 3 by 4, 0. Okay, so let us write some problems for practice. So in this way we complete our lecture and we will stop here.